In data science, one generally assumes one is given a sample with noise from some underlying space, and one wants to infer some properties of this underlying space from the data. In their seminal paper, Nyogi, Smell, and Weinberger assumed the underlying space was a smooth manifold, and they found the homotopy type of the manifold, assuming bounds on the noise and the density of the sample. Nyogi, Smell, and Weinberger formulated their result using the slightly probabilistic framework shown here. However, their probabilistic formulation and the ones we will discuss later on are equivalent. Nyogi, Smell, and Weinberger's result has led to many generalizations and inspired a lot of other work. In the generalization of Nyogi, Smell, and Weinberger, we consider sets of positive reach instead of limiting our scope to manifolds. We recall that the medial axis of a closed set in RD is a set of points for which there is no unique closest point of the input set. The reach is the distance between the medial axis and the closed set. A set has positive reach if the distance from the set to its medial axis is strictly greater than 0. The reach indicates how easy or hard it is to infer a shape from a noisy sample. If the reach is small compared to the noise, there can be several different reconstructions of an underlying space based on the sample. We now illustrate this using the following noisy sample. We observe two different possible reconstructions. The first option is a figure 8 where the crossing point in the middle is removed by lifting it slightly so that there is no self-intersection. Alternatively, two circles that almost touch tangentially. These two possibilities exist because the reach for both the reconstructions is very small. In our paper, we also extend the results of Nyogi, Smell, and Weinberger beyond the Euclidean space. We consider submanifolds and subsets of positive reach of arbitrary Riemannian manifolds with lower bounded curvature. The space of symmetric positive definite matrices and Grassmannians are examples of such manifolds which are natural stages for data. Symmetric positive definite matrices occur as diffusion tensors in magnetic resonance imaging, in image segmentation, and in texture classification, while Grassmannians are used for image matching and recognition. Although this video will mainly focus on the Euclidean setting, we will mention results in the Riemannian setting whenever they are not too technical. For subsets of Euclidean space, the setting is the following. We are given a general set of positive reach or a manifold of positive reach and a sample P such that the one-sided Hausdorff of distance from the sample to the underlying space is at most delta, while the one-sided Hausdorff of distance from the set to the sample is epsilon. We proved that if delta and epsilon or the one-sided Hausdorff of distances satisfy some bounds, there is a radius r such that the union of balls centered at the sample with radius r deformation retracts to the underlying space, S, where S will be used in this talk to denote a closed set of positive reach. In other words, the Čech complex of the balls captures the homotopy type of the underlying space. We showed that if epsilon and delta lie in the yellow region for manifolds or the blue region for sets of positive reach, then there is an R such that the union of balls with this radius centered at the sample captures the homotopy type of the underlying space. We also showed that for any epsilon delta pair outside this region, there are sets and samples for which there is no R such that the Čech complex of the balls captures the homology of the underlying space. We achieve similar results for subset, that is both submanifolds and subsets of positive reach of ambient manifolds whose curvatures are lower bounded by lambda L. Here you see the result for lambda L equal to plus or minus 2. The rest of this video is dedicated to illustrating the constructions of these optimality examples, mainly in the Euclidean setting. For the construction of our optimality example in the context of sets of positive reach, we let S, our closed set of positive reach, be a union of annuli lying in a row in R2. We denote the annuli by AI and we give them each an inner radius of 1 and an outer radius of 1 plus 2 epsilon. We note that we will only need a finite number of annuli to construct our optimality example. Next, we take a sample of the annulus. The sample consists of the circle centered at the annulus and the 2 points in red. Each point lies at a radial distance delta from the annulus. The distance between the 2 points is initialized at epsilon plus delta is equal to 2 r naught in the first annulus and thereafter determined inductively for the following annuli. We also initialize a purple third point symmetrically with respect to the first 2 points, as we now show in the figure. Our inductive construction is based on the circumradius of the 3 points we just described. Now we move on to the next annulus in the sequence. The circumradius from the previous annulus should equal half the distance between the red points in this annulus, and all other points and quantities remain as they were. We continue this inductive procedure where the distance between the points of the next annulus is equal to the circumradius of the points in the previous annulus. Eventually, we reach the annulus where the circumradius is at least 1 minus delta. Then we add a final annulus with 2 points whose distance is exactly 2 minus 2 delta, at which point we stop the sequence. In our companion paper, we show that we reach a radius of 1 minus delta in a finite number of steps, as long as we are outside the blue region shown here in the plot of epsilon versus delta. We now show that for any r, the union of poles of radius r centered at the sample has different homology than the underlying space of the annuli. For all small radii, the thickening of the sample has 3 connected components per annulus, 2 of which are spurious. When the radius of the sample reaches delta plus epsilon over 2, the number of connected components of the thickened sample drops to 1, but we also create a 1 cycle that should not be there. As the radius increases, the spurious cycle dies, but at the exact same moment, another spurious 1 cycle is born in the next annulus in the sequence. As the radius continues to increase, so does this trading of death for birth of spurious 1 cycles in sequential annuli. This process continues until we reach the final annulus in the sequence, where eventually the 2 1 cycles, 1 spurious and 1 real, disappear simultaneously when the radius is large enough. Note that once the holes have closed, the thickening of the sample has no more 1 cycles. This construction generalizes to spaces of constant curvature, which provides the proof of the tightness of our bounds in the Riemannian setting. The examples we constructed are in spaces of constant curvature. We use the sphere in the case that the curvature is positive and hyperbolic space when it is negative. Here we use the hyperboloid model in Minkowski space to visualize. The construction that proves the tightness of the result for submanifolds of Euclidean space is more complicated, but similar in flavor. The set which we want to capture the topology of consists of tori in a row instead of annuli as in the construction for sets of positive reach. The sample consists of tori with a rim cutout, replacing the circle in the middle of the annulus and 2 isolated points, similar to before. Recall that in the case of the annulus in 2D, we defined 1 point on the circle which formed the majority of the sample. Now moving to 3D and replacing the circle by a torus with the rim cutout, we instead define 2 extra points on the sample, on top of the isolated points, as shown here. As before, the distance between the 2 isolated points in the sample is determined inductively. In this case, by twice the circumradius of the simplex formed by the red and purple points. In the 2D setting, we found spurious 1 cycles that prevent the homology of the thickening of the sample from coinciding with the homology of the underlying space. In the manifold case, there are both 1 and 2 cycles that prevent this, as we now illustrate. We depict the first 2 and final tori and their samples in the sequence, and we note that there are many in between the first 2 and the last one. The top row shows the tori sliced open like a bagel, while the bottom row shows them sliced like a sausage, with the cutting plane going vertically through one of the sample points and the center of the torus. At first, there are too many connected components because the offset of the red isolated points in the sample doesn't touch the offset of the torus with the rim cutout yet. Then, in quick succession, there are a number of events. Namely, the offset of the isolated points start touching the rest of the set. Then the topological torus appears as a subset of the offset of the sample, but there are still extra 1 cycles. Depending on the distance between the isolated points in the sample, that is, at which torus in the sequence we look, we then find a succession of spurious 1 and 2 cycles for a short period of time for each torus. However, the example is set up in such a way that at least one of the tori in the sequence is plagued by spurious 1 or 2 cycles. We now focus on the individual tori to illustrate this succession of spurious 1 and 2 cycles. We now look at the initial torus in the sequence. The 2 offsets of the isolated sample points start touching, creating 2 extra spurious 1 cycles, 1 for each sample point. At this point, the top and bottom parts of the torus with the rim cutout start touching, and therefore a 2 cycle or a topological torus, which is not spurious, appears in the thickening of the sample. At the same time, the thickenings of the 2 isolated points in the sample also start to touch. This creates a spurious 1 cycle. At this point, there is still a tiny hole between the offset of the sphere and the offset of the torus with the rim cutout. This gives us 2 spurious 1 cycles in the complement, 1 for each ball. This corresponds to the 1 cycle in the space itself, which was created when the 2 balls started touching the offset of the torus with the rim cutout. And now, these 1 cycles are killed. We now change viewpoint and go back slightly in time to illustrate the merger of the thickenings of the isolated points in the sample. Here we see the birth of the spurious 2 cycle. This is not easy to see or to visualize, but is essential to our construction. We will revisit this spurious 2 cycle several times and from various angles. Returning to the original viewpoint, we see a 2 cycle being born at a cost of a 1 cycle disappearing. We stress that this is a spurious 2 cycle. We now illustrate the spurious 2 cycle from the inside. As in the annulus case, we trade death in the torus we are viewing for the birth in the next torus in the sequence, which we previously showed in the overview. The hole in the middle of the torus is eventually filled up. Now, we move on to the next torus in the sequence. Because the distance between the 2 sample points is larger, the spurious cycles which are associated to these points occur later. In particular, the 2 offsets of the isolated points start touching exactly when the 2 cycle was killed in the previous torus. We now skip many tori in the sequence and show the final one. The 2 isolated sample points on the black circle are now antibodal. This means that the spurious cycles associated to these points occur at the very end. We change viewpoint now to better show the topological transitions. We see the 2 spurious 1 cycles in the complement persisting for a long time. These give rise to 2 spurious 2 cycles which get filled in almost immediately. So we have seen that the thickening of our sample never captures the homotopy or even homology type of the underlying space. Therefore, the bounds on the homotopy reconstruction which we gave in our companion paper are tight. We hope that the viewer has enjoyed the beauty of homotopy inference and its limitations.